Okay, good morning. Welcome to this 19th session of Memory Design and Test course. And we would continue our discussion with flash memories today. But before we start, there's this announcement, which I made last time also, that the next class is uh, as a guest lecture. We will have Kalyan Kavalepurupu, who is a director at Micron, Hyderabad. He will be coming over physically on campus and conducting this session on Thursday. The regular class timings, 11:30 a.m. 11:30 a.m. to what time we do not know. We'll hopefully finish within 1 o'clock. That is the regular class timing, but it may spill over a little bit because, as I discussed last time, he's a very knowledgeable guy, and it's also an opportunity for you guys to interact with him and make a good impression, if that is the right word. Make a good impression so that he's willing to hire students from here and as interns and then as employees. We're also looking forward to a more deeper collaboration with Micron India at a university level. So one purpose of his visiting us physically is also that we are looking forward to that kind of a collaboration to happen. So I would say that this is one session that each one of you should be attending physically. Even if you are not in the hostel, if you're staying at your homes, come whatever may, you have to be on campus on that day, on Thursday that is, and be attending this session physically. It would be good to interact with him. He will be around. He is coming just for this class, and then I took this opportunity to also invite him for the next day. So if you're presenting posters on Friday, you can actually also invite him to visit your poster and tell him that, okay, I'm in this track and why don't you visit us tomorrow? I will show you about my work. So that could be something that you could actually tell him separately after the class. So it would be good to interact with him. He's a good person, very keen to have a collaboration, very keen to ensure that IIIT Delhi students are at Micron. He takes care of them well. So this is something where each one of us has to be there on Thursday. Any questions? Any doubts? So the expectation is abundantly clear, it seems. Is the benefit clear? Class?
Yes, sir.
So please make sure that each one of you is there. I will also invite the DVD class list. Those who did DVD with me last semester, I would also invite all those students. A007 is a big enough room to house all the students of DVD plus MDT. So most of you are common anyways, but it will be able to house all the students. I do not want to have even one seat vacant because it's an opportunity that I do not want any one of us to miss. So if you know of friends who are interested in VLSI, please ask them to come. If they're planning to take a job in VLSI domain in the next semester or the semester after that, then they should definitely be there. Okay. So not exactly a job in Micron, but it's an opportunity. You get to know how the industry works. You can ask him questions. I will request him to keep, say, 15 minutes as an open question hour session where you could ask him anything about his career, about his, anything about opportunities at Micron, whatever you want to ask, you can ask him. I will request him to keep that kind of time also in that session so that all of you can gain as much as you can. So please make it a point that you are there in the class on Thursday, physically there in the class on Thursday. Okay. So now, what were we doing in the last class? Before we get on to flash memories again. So he will be talking about flash memories. So I would say if you accidentally missed the last class, please review both the flash. So yeah, last class's lecture and today's lecture. Please review that. It will make it easy for you to understand what he's talking about. You will be able to contextualize it better, and therefore you will be able to ask intelligent questions. If you come there without, attending these two sessions, today's and the previous one, you will understand what he's telling. He's a good speaker. He explains well. So he also conducted a tutorial in VLSI design this year, VLSI design conference this year. So he's a good speaker. You will anyways understand what he's saying. But if you're getting exposed to that knowledge for the first time, you may not be able to ask intelligent questions. So a very strong suggestion that at least this lecture and the previous one, you should be alert. If you by chance are not alert, please review the sessions before you come for the next class. It would help you. It would help you ask intelligent questions. Even if you're not able to do it, you should come. But it would really help you if you're able to study and then come. Okay. So what were you doing in the last class? Let's see how many of you have already studied.
So we were looking into the non-volatile memories. You talked a bit about EEPROM and EEPROM, and after that we were looking to Flash, and how we use the floating gate to change the VT of the device. Then we were talking about the VT curves, how the current will change, and we'll store four different like 2-bit values, like 4 different values. And after that, yeah, till that much I remember.
Okay. Anything else anyone wants to add? So how are we storing those 4 different VT values in the system? So someone other than Faisal. How are we changing the VT of the device? What was the physics that we were using?
Using the floating gate.
Sorry, can you be a little louder, Dipank? Dipank, I could not understand what you were saying. Yeah, then put it in the chat window. What is the physics that we use for read and write inside practically write in the flash cell?
We increased voltage at the gate to induce charges in the floating gate.
Okay, so what is the physical phenomena, Anushka?
Not sure, sir.
We talked about hot carrier injection and FN tunneling.
Yes, sir.
So that is the physical phenomena through which we are able to transfer electrons or charges into the gate or out of the gate. So what is HCI? Hot carrier injection. Who can explain? What is hot carrier injection?
We apply gate voltage at gate to basically pass electrons at high speed, which get stored in the substrate or the dielectric, you can say, and basically they change the intrinsic property like the threshold voltage in turn. If there are like more carriers, then there would be lesser threshold voltage, for example. to.
So yeah, partially on the mark, but a little bit off it also. What happens is that in advanced technologies, if we apply a high VDS, then electrons or the carriers start to move from source to the drain region. As that happens, as the carriers move from source to drain region, across along the VDS electric field or a field that is generated because of a particular VDS being there, they gain momentum, they gain kinetic energy. So they are very high energized. That is why the use of the term hot. Just give me a second. So that is why the use of the term hot. And then because we have applied a high gate voltage, we say that there is a vertical pull also that is applied on the electrons, and they get injected into the oxide gate region, whatever. Now, the fact of the matter also is that when electrons are kind of pulled up into the gate region, they get trapped in the floating gate setting. They get trapped in that floating gate. So when electrons get trapped in the floating gate, what happens? What happens when you want to attract more electrons in the substrate region?
So if the positive charge is trapped in the floating gate, then we need to apply less gate voltage to attract the electrons. And if the negative voltage is if the negative voltage was trapped in the floating gate, then it will repel the electrons in the substrate region to form the inversion layer. Then we have to apply more gate voltage.
So whenever the hot carriers get injected into the source or into the gate, what is happening? So this is the oxide. Let us say this is your floating gate, another oxide, another gate, whatever. Okay. So the top one will be called as control gate. This is floating gate. Oxide 1, oxide 2. And you said that there were carriers which were injected from, so very high energy carriers. They reach this region, but because there is a vertical field also applied, they get a vertical push and they can get trapped in this floating gate. So if this inversion layer was of electrons, what are we trapping in this floating gate?
So electrons will be trapped.
Electrons. Yeah. If this inversion layer was holes, what are we trapping in the floating gate?
Then the holes will be.
Then we are trapping holes. So what that means is whatever is the majority carrier, whatever is the carrier in the inversion layer, that is what we kind of trap into the floating gate. So if now you want to attract more attract more similar charge in the substrate region, you would need to apply a little extra voltage because the like charge is already there. Like and like charges will repel each other. If there are already electrons in the floating gate, they will not let more electrons to come to the gate, to the surface of the device easily. So VT would increase.
Yes, sir. So can we just like say that if in the hot carrier injection the VT is increasing always?
You can say that.
Yes, sir. Okay.
Because hot carriers come, you start to talk about hot carriers only when you're talking about inversion layer being there and actually charges being moving at a very high at very high speed, having a lot of kinetic energy with them.
Yes, sir.
So it is always the HCI will always lead to increase in VT. So how do we then reduce VT? How do we remove electrons from the floating gate?
So by applying the this point we discussed in the last class, by applying lower voltage at the gate and the source, so the charges will like this, they will be discharged from the floating gate.
See, to attract electrons to the floating gate, what did you do? You applied a very high positive voltage on the control gate. Now to repel electrons from there or to take away electrons, you have to apply a very strong positive voltage in the source or drain region, so that electrons can go there. But they will not now go because of HCI. HCI is only because there are high energy particles in the channel region. When you apply this kind of voltage, then what happens is you initiate what is called as FN tunneling. And that is how you will remove the charges from the floating gate there. Is it clear?
So can you please elaborate it a bit more? Like I understand FN tunneling but how the charges are, like the band is the energy that the electrons have to move from one energy level to the other energy level is lesser now. So they will easily go from lower to higher level and take out discharge from the floating.
Yeah.
Okay. Okay.
Okay. So any questions from the last class? So then, we also discussed that we could have different duration of for which HCI could be implemented. We could have so many different variants of all these techniques, and therefore we could have multi-bit or multi-level cells also over there. Huh? You remember? So just give me a second. Disruption. So where were we? Can someone just bring me back? Any questions from the last class? Any further questions from the last class?
Just to confirm, each transistor would represent 2 bit, right?
Not necessarily. Each transistor can represent just 1 bit, or it could actually represent even more than 2 bits.
Okay.
So when Kalyan will talk about the most advanced flash memory on Thursday, you will see that there could be many more bits that it could be saving in every transistor. And there are advanced schemes, which I'm not going to talk about, only he will talk about in his class, which can be used to, add more, how do I put it, resilience, error resilience, even despite scaling in technology. So he will talk about that on Thursday.
Okay, sir. Thank
you. Faisal?
So when we were talking about in the non-volatile memory part, we were talking about the security. So can you please elaborate it a bit more? मेरे को इतना समझ नहीं आया actually clearly कि delayering करने में Yes, sir.
Okay. So if I want to find out what was the code written in a ROM, what do I
Yes,
need to
sir.
do? I need to take the chip, I need to delayer it, and I will get a fair idea of what the code is written. Can I?
Yes, sir. Yes, sir.
But can you do that in a flash?
No, sir.
Yeah.
नहीं फ्लैश में सर जैसे
How can
फ्लैश
you?
का हम एग्जांपल देखते हैं कि जो हमारा एसडी कार्ड और ये फ्लैश मेमोरीज होती है तो हम उसमें तो रीड और राइट करते ही हैं, देखते ही है ना। मेरे को एक्चुअली जो प्रैक्टिकली जो हम यूज कर रहे हैं ना उस वजह से मैं कंफ्यूज हूँ।
Okay. So let us say that there is a secure area in your, so there is a secure ROM that you cannot access, or a secure area in your flash that you as a external user cannot access. So when you purchase a flash memory, let us say 128 GB, 128 GB entirely is not available to you, is it?
Yes sir, yes sir, yes sir.
Some part is only available to the operating system there.
Yes sir.
है ना? So when that happens, what is it that we are worried about? The part that is available only to the operating system that no one else should be able to access.
Okay. Okay sir.
है ना?
Yes sir.
For a flash, you could still do that, but for a ROM, someone can actually delayer the ROM and find out what is contained in that operating system zone.
Yes sir.
Then flash is definitely reprogrammable in the sense that even if you want to store your operating system data there, you could reprogram it after some, if there is a bug, you can always fix it in the flash. If it was
Yes
a
sir.
ROM, you cannot fix anything. It's already done.
Yes sir, yes sir. Yes sir. Okay. And when we are talking about the electrically programmable ROM, then we can program it by using the fuse. So
Yes, that is only once.
yes sir.
You need an electrically erasable and programmable ROM, EEPROM.
Yes sir. And can you elaborate about the security of EEPROM and EEPROM, sir?
So they're equally secure. EEPROM, again, one can always delayer and find out the fuse situation.
Okay.
है ना?
Okay, sir. Yes sir, yes sir, yes sir.
है ना? So that is the thing.
Okay, sir. Thank you.
Just give me a second. There is some emergency somewhere. Just give me a second. Okay. So in terms of security, when we were talking about EEPROM and EEPROM, again, it was the same thing, where we were talking about the fact that when it is a one-time fused programmable ROM, then you can one-time fused programmable memory. Then again, you can delayer and find out where the fuses are blown off, so you can actually find out. But if it is an electrically erasable and programmable, then you can't. So flash is being an EEPROM, so flash is therefore in those terms more secure. Is that okay?
Yes sir.
Okay. So now we come to look at what flash architecture is about. So again, we have row decoders and column decoders, and just like the DRAM, the address bus is shared here also. So what does that mean? When I say that the address bus is shared, what would that mean?
Square is structure.
Not okay. So either yes, it is either we can say it is a squared row, a square array, or we could say that it is something which is or we could say it is something which is where you will have to send address in multiple phases.
Less resources.
Yes. Again, this is very critical over here because flash is always off chip. If the flash would be on chip, then again, you need not have this multiplexing of row and column address on the address bus. But if flash is, how do we put it? off chip, then there are a number of pins that are involved there, and that is what needs to be taken care of. So again, over here we have word line which goes on the control gate now, and the bit line which is connected to the drain. Is this clear? So notice there is this source switch. Source switch means ground connection coming from here. And so what kind of a flash is this? This is the control gate on the word line connected to the control gate, and bit lines connected to the drain region. So what kind of flash is this? NOR or NAND? What kind of flash would be this? Hello? Yeah, why is this NOR?
Because
स्लाइड पे लिखा हुआ है.
अच्छा कहाँ लिखा है? नहीं सर, स्लाइड कहाँ लिखा है?
स्लाइड के टाइटल पे NOR लिखा हुआ है फैसल, but why is it NOR?
सर सोर्स कनेक्टेड है बिट लाइन से, तो वो देख के मैंने.
See, over here, every device is connected to bit line on one side and source on the other side. So all the devices are in parallel to each other. Any one of the device allows current to flow, bit line would discharge. Because that is the logic that is being applied, this is NOR.
Yes sir.
Okay. So when we have this NOR flash, what is being done? To do the read operation, what do? We just take the bit line, the word line to a level which is between the VT of say 0 and 1. Okay. Now at this particular word line level, all these devices, they will sync current, and the devices over here will not sync current. The cells that sync current, they are said to have, let us say, 0 stored on them. The other ones are said to have 1 stored on them. Is it okay?
So ये वही सेंस थ्रेशोल्ड वाला पार्ट है ना?
Sorry?
जिसमें डिफरेंट थ्रेशोल्ड चाहिए थे हमको, हाई वीटी और लो वीटी, जो उनका एक बीच में मार्जिन होना चाहिए.
Yes. So हमने यहाँ पे we've ensured that the spread of let us say cell storing 0 is 3 volts, the cell storing 1 is 7 volts. So there is a huge margin in between them, and we are keeping word line at somewhere in between them. Okay.
Yes.
How do you do a write? How do you do a program? So that was the read operation. How do you do a program or an erase? So what happens is, let us say there are so many of these word lines there. You would, to erase this thing, you would put word line at -10 volts. And you would put bulk at 6 to 8 volts. What will happen?
FN tunneling will happen. So because
FN tunneling will happen. Yes,
it,
FN tunneling will happen, and all the electrons that were there in the floating gate will be repelled into the bulk region. Bulk has a high positive voltage. Control gate has a very high negative voltage. So all the electrons in the control gate will get repelled, and you will have cell VT again, which is in this range. Okay, when I want to program, we already discussed this last time also. When I want to program, word line is at plus 10 volts. Bit line is at, let us say, 5 volts. The other bit line is at 0. So what is happening?
Charge will be trapped.
Yes, you create a high VDS across the gate, across the device. So charges are energized, and then you have a vertical field also. So charges, electrons are attracted to the gate. They will breach through the gate oxide and enter into the floating gate there. As a consequence, VT would increase. Is this clear? Any questions?
So what does F mean in this?
Floating.
Okay. So why are we keeping select line SL as floating?
So it is not select line, it's source line.
Okay, sorry.
Yeah, the source line is also left floating because you are doing FN tunneling into the bulk.
Yes. Okay, okay. So we want them to escape via bulk and not
Bulk.
through source.
Okay.
Obviously they won't be able to. Okay, got it.
Yeah. And then that is the read operation that we just discussed.
सर जस्ट फॉर क्लैरिफिकेशन जो 1 से 3 वोल्ट था वो जो ट्रैप्ड हो रहा है उसका वोल्टेज की वजह से है 1 to 3 वोल्ट और 7
1
to
to
9
3 volts VT इसलिए रह गया बिकॉज आपने जितना भी चार्ज इसमें था आपने उस सारे चार्ज को भगा दिया.
ओके
आपने उस सारे के सारे चार्ज को रिपेल कर दिया फ्रॉम द फ्लोटिंग गेट एंड इट हैज गॉन इनटू व्हाट डू वी से
बल्क इन सोर्स साइड.
यस. ठीक है.
यस
So the layout of such a cell appears something like this. The green one is the source line that is sent through the diffusion layer, and yellow one shown over here is the, let us say, control gate. Floating gate is shown with this light gray kind of a thing, and then there is isolation between the cells. Now this is STI. And do you see that with every cell, there is a set of contacts that are there and everything that is there? So what happens? It takes a little bit more area than you would have desired. This is how the cell would look like. Sorry. This is how the cell would look like. You see the control gate. This is the control gate over there. And these are the floating gates. The control gate is one continuous line. Why is that the case? Because it is the common word line. This is the row. This is word line view, which is cross section at this place along the B axis. So control gate is continuous. Floating gate is just above the device, and this is the source and drain region there. Now, if I intersect or intercept from here, then this is the view that I see. I see the contact for the bit line, and I see the source drain region for the device also there.
So the thin white strip between CG and FG is that the dielectric, very thin.
I'm sorry?
Sir, the dielectric is very thin, like
This one.
and in between CG and FG also.
Yes, this one also.
Okay. Got it.
Okay. Any further questions? Is this clear? Okay. So now in a NOR flash, then what you do? You organize the entire memory into blocks. And in every block, you have these NOR cells which are arranged with the help of row decoders and everything. And this is the, every cross section over here represents such a bit cell, such a flash cell over there. When you want to read, now let us say you were storing 2 bits in this memory cell. Let us say, if you are storing 2 bits in this memory cell and you want to read, then there are 2 ways that you could read. One way is that you apply 1 voltage on the gate and then measure the current that different bit lines are discharging. So what does that mean? That means that the current that is consumed by a cell which is, let us say this is 0, 0, 0, 1, 1, 0, and 1, 1. So current consumed by 0, 0 is obviously 0. 0, 1 is equal to IC2. 1, 0 is equal to IC3, and 1, 1 is equal to IC4. If you can identify what is the current that is being sunk into the memory cell, you can tell what data you are storing, what 2 bits you are storing in your memory cell. Is this part clear? So you will need a current sense amplifier, current mode sense amplifier. Is the left figure clear?
Yes, sir.
Now, when you want to read, what do you do? When you want to read in the voltage mode, what do? You say that I want to measure when is IC getting sunk in my particular cell. So let us say for one cell, IC got reached at VG4 itself, and another cell, IG got reached at VG1. So what this means is that this is, let us say 0, 0, this then is 1, 1, and you could say 0, 1, 1, 0 over here. Clearly, when you operate in voltage mode, you have fixed the IC per cell. So you require lesser currents. It is lesser power, and also, in one go, you could be able to make out a lot of stuff. So parallelism is also high. Are you able to see this? Any questions?
So just for clarification, with one current measuring, we can read around four states, right? We can read that 4 states only with one current measures.
Only with one current value, we can reach we can identify what voltage will my cell sink that kind of current, and I can kind of estimate the VT of my device.
Yes, sir. From there we can decide 0, 0 or 0, 1.
Yeah.
So okay. I'm just confusing in if there will be 4 devices connected and to 1 bit line, and that case would not create because the word line would be selected only.
I'm sorry.
Yeah, got it, sir. थोड़ा confuse हो गया.
ठीक है. So if we say that we were doing, say, let us say voltage mode read operation, then what does the circuit looks like? What does the circuit look like? It could appear something like this. I want to sync, let us say, some cell current, IBL. Okay. So this is my bit line, and I know what is the cell current that is being sunk here. Okay. With this cell current, I kind of put a bit line limiter that more than this current will not be sunk by the bit line. And there is this CBL, which I discharge with the current of IC. And when I start to do that, I kind of mirror it to get the current KIC go in this arm. A voltage would appear over here. Okay. A voltage would appear over here. And depending on IR minus KIC, there could be some charge that would flow from a high voltage sense amplifier into this region. This output is amplified. So this ID is then amplified through this amplifier stage. You see, यहाँ पे 1 है, it is H over here. So this is amplified with over H times over here. And when the steady state is reached, we simply measure the VG. VG at this point tells me what is the voltage at which that kind of current is being discharged from my bit line. So I will be able to estimate whether it is V4, VT3, VT2, or VT1. Questions?
So by measuring at the end, we are measuring the VG, and by measuring VG, we are saying what is the, yeah, okay, sir.
Is that okay?
Sir,
Yes.
ID, who is controlling ID? Can you tell again?
So IR, I have a reference current. K times IC plus ID should be equal to IR.
Okay, so as KIC varies, so does the ID, and then IC amplifies to give us the output basically. Okay,
Yes.
got it.
Is it clear? So we're just amplifying K times once and then doing this subtraction at this reference voltage and then multiplying it with H times.
So how we are deciding this K at this H value? Like on what basis?
I'm sorry?
How we are deciding this K value and H value, on what basis we are deciding these values?
That is the kind of current budget, the speed that you need, and so on. What is the
So
power
for-
budget that you want to keep, and what is the speed at which you want to operate?
Okay. Sir.
Because if the K is large, a large amount of current would flow. The references, so it depends on the current that you want to sync and the sensitivity of that you require of your circuit. All these factors.
Okay, sir.
Okay.
One basic doubt: why did you say that current mode of read operation is not parallel? While okay, I got it. Why voltage would be parallel, but why that current mode would not be parallel?
Why current
Because since we are only applying one gate voltage and it is giving us 4 different currents, so why can't we sense them simultaneously?
So okay. So if I want to sense them simultaneously, I will need to have 4 sense amplifiers,
Yes, sir.
and then I can sense them simultaneously. Yes.
So, sir, what is the contrast between parallelism in both the
Contrast
gates?
is this kind of current is flowing. Over here, you have limited the current to IC.
Yeah, the power dissipation is
Power
one
dissipation
factor.
is a clear contrast.
Okay, so that is the only thing.
Yeah.
Okay, thank you.
Okay. Now let us look at the flash memory. We can use exactly the same things in here also, but in the flash memory, you are kind of in a NAND flash memory, you actually have a string of devices connected to each other in NAND structure. So 16 or 32 cells may be connected as with one select transistor. And program BT, let us say, is greater than 0 and erase BT is less than 0. Interestingly, the source and drain region over here now do not need a contact. See, in the NOR flash, you need a contact for the drain where the bit line would connect and a contact for the source where the source line would connect. Over here, we have bit line select and let us say ground select signals. There are two regular MOSFETs that do not have the control gate and everything kind of mechanism there. And only they connect to source or they connect to the bit line. There is no requirement of contact in between the flash cells now. So the density of the NAND flash is much higher than that of the NOR flash. Is this thing clear?
Yes, sir, since we are not using the contact, then we can say that it is more denser.
Yeah.
But then how the operation will happen, sir? Can you?
Yeah, that will come to anyways.
Okay, sir.
So now look at it like this. You simply have word lines and there is no need for having any contact over here. So these gates can actually come much closer. So these gates can actually come much closer and you can have a denser memory cell. NAND flash is therefore multiple times denser than the NOR flash. Okay? In a NOR flash, you had one transistor per bit, whereas in a NAND flash, you have 18 transistors. The source select and the gate select signals are extra. So 18 transistors per 16 bits. This therefore is much denser. Is it okay? Clear?
Yes, sir.
Sir, can you please explain once again how the gates are coming closer?
You do not need a contact in here now. See, in the NOR flash, there was a contact that was required at the drain. What contact was that for? Bit line. And then you also needed a source line to be run.
Yes, sir.
So over here, they're saying there is only one contact over here for the bit line and one contact over here for the ground. No other moving out of the, what do you say? So,
okay, sir, got it. Yeah.
because you have lesser contacts, you can be much denser.
Okay, sir.
So this is how it appears in the kind of a layout where after every say poly you had a contact or a source line running in, and over here for the NAND it's completely just a string of devices, no space for contacts.
Yes, sir.
So for the NOR flash, contact is what limits further scaling of area. NAND flash can actually scale down at the same pace as the poly to poly spacing scales down. At least that was what the initial thought was. And you see, this is how so many transistors this is how your NAND flash is denser. Okay. Another cross-sectional image where you see that different word lines simply go like this. There is a source line that connects to the source, and there is a drain line which connects to the bit line.
I doubt regarding the previous slide, sir. The final reason I'm audible, sir.
I'm sorry, दोबारा से बोलो.
Sir, I'm audible.
Yeah, you are audible, but a little low on volume.
Sir, I wanted to know in the previous slide, the main reason for the NAND to be denser was the poly spacing.
So
I'm not convinced with the reason of the NAND to be more denser. Can you just highlight once more?
okay, because now let me repeat. See, in a NOR flash, you had a poly, you had a contact for the source, and you had a contact for bit line. Am I right?
Yes.
Then there would be another poly over here. So what is the spacing between two polys? Contact plus 2 COPO spacing. So
Okay, sir.
one COPO here, one COPO here, and the contact width. Whereas if there was no contacting in between,
As in the case of NAND.
yes, as is the case of NAND, then the two cells can actually be much closer. You just need
Because sir, you also mentioned in one slide the number of transistor per bit required in the NAND or more.
yes. Over here, we said if we're storing 16 transistors, we have 16 transistors in this string. There are 2 extra transistors for the gate and the bit line select, for the ground and bit line select.
Okay.
And
despite
remaining,
having these 2 extra transistors, NAND are denser because of that contacts are not there in between them.
yeah.
Okay. No doubt. Thank you.
Okay. So what are the scaling challenges linked to a NAND flash? So I'm writing something, you should actually ask details from Kalyan in the next class. First is performance. See, as you scale down, the currents would reduce. Second is VT distribution. As you scale down, because the floating gate is now smaller, mismatches will happen more prominently, and there will be a challenge of VT distribution over there. And then since we are applying very high voltages, so you're talking about plus 10, minus 5, or minus 10 and 6 to 8 volts on the bulk, talking about very high voltages put across the control gate to the bulk part. So with these high voltages, there can be a lot of issues on reliability. So in NAND flash or even in NOR flash, reliability is something that you should always be extremely careful about. So again, when you want to program, what do? So in a NAND flash for programming, so in a NOR flash, what did we say programming with?
Hot carrier and
HCI.
yes.
But in a NAND flash, we actually do this also with FN tunneling. We simply create an inversion layer here, 0 volt on the bulk and 18 to 20 volts on the control gate. Electrons simply get the energy to jump into the float gate. If you want to erase, you simply change the connection. 0 goes on to the control gate and 18 to 20 volts, that is something of similar order, going on to the bulk. So all the electrons are thrown out from the float gate into the bulk again.
सर ऐसे तो हम फिर नॉर में भी
ऐसे तो हम
सर नॉर में भी कर सकते थे हम जिस तरीके से रीड और राइट कर रहे हैं.
Yeah, but FN tunneling is much slower than HCI, ना?
Okay. तो तो हमने हॉट कैरियर उस बार प्रोग्रामिंग के लिए वो यूज किया और ओके
हाँ हाँ okay. So now it appears okay at a cell level, but you being memory designers, you also have to see what happens to the cells in the same row which are not to be selected. So आपने कहा I want to program, let us say, this particular cell. So its word line would go to 18 volts, but the same word line is going to so many other columns also. So how do you prevent write in other columns? How do you prevent write into the adjacent ones? You say that I will apply a different voltage on V pass and a different voltage on the bit line. If you apply a different voltage on the bit line, what happens?
The charges are conserved in the other column.
When we apply this 8 volts over here, we in a way kind of ensure that the bit lines which or the source and drain which were kind of left floating are not really floating there then. They have a distinct voltage on them, and because of that, what happens? This 8 volts, so look at it like this transistor. The gate is at 10 volts, bit line is at 8 volts. What happens to this internal node over here? What would appear here? If the VT of this device is 2 volts, what will appear on this node?
8 only.
8 volts. So this 8 volt will actually, you will see, pass to this last device. Now, when the 8 volt is there on its source and drain, what happens? You want to apply HCI. But now you cannot apply HCI. Why? Because 8 volt has got transmitted over here until everything, and therefore the kinetic energy or the inversion layer that is formed will not have that kind of a thing happening. Is that okay?
Yes, sir.
And you could actually, so okay, for the flash memory, there is this one important figure of merit, which is like this figure of merit, which is like what is the ratio of gate coupling? What is the capacitance of the gate versus total capacitance? Okay, that needs to be taken care of. Now that was one scheme where we had to apply, now how many voltages are we talking about? 0 volts, 8 volts, 10 volts, and 18 volts. 4 voltages we're talking about. It means 4 different voltage regulators. Can I do something else? So there was this paper, a very old one at that, which talked about self-boosted flash. So what happens there? First of all, BL1 recharges all transistors to VDD minus VT. And if I put this at VDD, then BL1 will precharge everything to VDD minus VT. Everywhere it will become VDD minus VT. Am I right?
Yes, sir.
Then SSL goes off. What happens? All the channels, all the channels of all the transistors on BL1 become floating.
Yes, sir.
So in a way, you used VDD only, you reduce the supply voltage there, instead of using a different VDD, and with some constraints, you are actually ensuring that this particular cell is not programmed. That this VDD is such that you do not program this. Is that okay?
सर ये वाला पार्ट नहीं आया समझ में।
क्या नहीं आया बताओ?
सर जैसे हम बोल रहे हैं कि वर्ड लाइन अगर हमारा 18 वोल्ट है तो सारे पैरेलल उसमें भी जाएगा, और आपने कहा कि बिट लाइन का वोल्टेज हम चेंज करके उनको प्रिवेंट कर देंगे कि उनमें डेटा करप्ट नहीं हो हमारा। तो
So let us look at it again.
यस
हमने पहले यहाँ पे VDD रखा था. We had kept VDD here and we are taking VDD to 0 when I want to write into this particular cell.
यस सर।
So when it was VDD, what was happening at all these places? VDD minus VT must have got transmitted.
यस सर।
Not exactly VDD minus VT.
DD
V pass, which is 10 volts minus VT.
Yes sir, yes sir.
If VDD is less than that, then entire VDD would get transmitted. If it is more than that, then that little part would, then VDD minus VT will get transmitted.
Yes sir.
Okay. So what happens? You taken this to 0, then as soon as you take this to 0, it is 0 everywhere. If it is 0
Yes.
everywhere, what happens? FN tunneling starts.
Okay.
Over here, that doesn't start because over here it is VDD minus VT.
Acha. Okay, okay sir.
You not put the device in inversion region at all.
Yes sir, yes sir.
So the programmation will not happen.
Okay, okay sir.
Okay. Any further questions on this? Okay. So then if you look at the timings, if we start to look at the timings, then chip enable is low. It means your chip is active. Chip enable low. Chip enable bar is low. So your cell is active. Then address latch, column latch, everything, these are coming. Command latch, address latch are coming. So when the command latch comes, your IOs, you start to latch the command. When the address latch comes, you start to latch the address of the column, and then in subsequent cycle of the row. Okay? And then you wait for data to be transferred for this column and for this row. Okay? And you do a data out. Is this clear? I will, okay, let me remove mine and show the. So this is the first phase, the command phase, then we have the address phase, then the data transfer phase. And once the data transfer has completed, you kind of say, okay, we will read out. This, though it has been shown to be a small width, is actually a long phase. Okay? Now, when I want to program, what do I need to do? I again need to give a command. I need to give a column address and the row addresses. And then I start to send my data that I want to program in the memory. Okay?
Yes.
So we are able to, okay, so there is also a, would you say, a counter or something which tells us that programmation is completed or not. Once it is completed, we start the next operation there. Okay. So now let's look at, if we were to design a 1 gigabit flash memory, how would we organize it? So first thing is, that 1 gigabit thing will be separated into two banks of 5 and 2 megabits, let us say. And in each bank, there will be blocks. What is a block? Suppose your memory cell had 32 cells in it. So the block will have 32 cells. And the block would have 32 words. Okay. So this is 32 then. Each block, there are 32 words. All cells on one word line form what is called a page. All of them will get programmed together. At any given point of time, when you select, say, one word line at 18 millivolts to program, all the cells, all the transistors on that particular row would get selected and programmed all at once. Is this clear? Now, why do you think over here we've added 32 bits? Over here also 32 bits. Why? Why are these 32 bits extra bits there?
Word line cells all are programmed together. Is it due to that?
The sense amplifier is also connected to them. You heard about error correction codes?
Yeah, just heard about.
Huh?
Just to know.
When I spoke, you got to know. Huh? Or you knew about it earlier?
Just know the name and see.
You just know the name. Okay. So error correction codes are used so that if there is some error that is script and either at writing or during read from a particular digital circuit, by storing the codes there, I can actually decipher what the error was. First, I can first detect that there is an error, and then decipher what the error was and correct the contents of the memory. This is extremely necessary for Flash. There was a point in time it was also extremely necessary for, what do you say, DRAMs. It adds error resilience in the presence of noise. So you will see that error correction is used widely. Then this set of 32 pages is called one block. Okay. Now, when you erase the memory, so when you program row by row. So you program every page in one go. But when you erase the memory, you erase the entire block.
So that means that particular row in every page, erasing the entire block.
Every row, yeah. So all the 32 rows, 32 cells are part of the block, and not just 32 cells, all the rows of those, all the 32 rows of that NAND cell, if the NAND cell has 32 bits, are a part of the page.
Okay, sir.
What would happen if you increase the page size? What would happen if you increase the page size? सॉफ्टवेयर टर्म्स में और इधर भी Hello. So as you increase the page size, as I said, the entire page would be deleted. Oh, as you increase the page size, uh, your actually line lengths, the data that you're fetching from the main memory, from this flash into the main memory or elsewhere, increases. So the delay would increase, but the line length is essentially increasing.
Sir, would that also mean lesser number of bits will be required for error correction?
Why would you say that?
Sir, what does it depend on, the number of bits in error correction? Is that the size of the word?
Yes, the length of the word. For example, if the word is 32-bit wide, you will need for a SecDed code 5 error correction bits.
So it's like parity generation, something like that.
Parity is always 1 bit.
Okay.
But error correction code generation is dependent on what do you say? How many bits your database has.
Okay, sir.
So we already saw the sense latches and the data as is. And this is how my one logical page is broken into 2 physical pages. So now what we are saying is that there are 8K plus 256. 8K plus 256 bits that are being read on the left side and same bits that are being read on the right side or written from the left and right side. So over here, if I say that this is my flash memory, 125 millimeter square, 1 gigabit flash memory, then there are bit lines that are running like this. Over here, in every block, how many word lines do I have? 32. And there are 1024 blocks. So there are 32K word lines in total. And below the sense amplifiers, you have what is called as a page register, which is a memory, which again includes ECC. It's a memory with ECC. And this ensures quick or decoupling of the speed of the flash from the speed of the processor or the processing system altogether. Because the burst mode and everything can actually be implemented in this page register itself.
Sir, is this composed of SRAM cells?
Sorry?
Stage register is composed of SRAM cells.
It can be SRAM cells, it can be flops. Ideally, because this is a large number of registers, this is a large number of storage elements, you would use an SRAM. An SRAM would be denser. But SRAM would mean a little bit extra complexity also. If you do not want to go into that complexity, you can just make a register bank. Anyway, this cube is very dense.
Okay.
And this is the logical view of this. What we are saying is there is a cell, there is this concept of word, then there is a page. Pages all the bit lines, all the cells sharing the same word line. That is a page, and a block is a group of multiple pages where the bit lines are there are multiple bit lines and both multiple word lines in there. Okay. As I said, entire page is programmed at once and entire block is erased at once. Okay. If you increase the page size, let us say, so यहाँ पे इधर देखते हैं, we increase the memory size 8 MB, say we went to 16 megabit. I maintained same page size and block size. What happens? Read per page remains same because the size of the page had remained same. The program per page remained same, and erase per block, the duration remained same. Now, if I go to a larger memory with, let us say, larger page size now, larger block size now, then you will notice that this timing, program per page timing, can start to reduce a bit. Why would that be the case? Hello?
So because more number of cells have been programmed at once.
Because your page size has increased. So if you wanted to update a particular file, you now need lesser program operations. If you change the block size, then what happens? Then you notice the erase time over here has reduced. Because you erase the entire block in one go. Now that size has increased, so the erase time has reduced. Over here, we saw a significant reduction in, how do we put it? Program time. We also saw a reduction in page time, in the erase time, but that was the major chunk over here, and that has reduced. Okay. So if you're talking about, I'm sorry, I'll just take another 1 minute, because I want you to be prepared for Kalyan's lecture. That's it, just 2 more slides. We're talking about 125 millimeter square, 1 gigabit NAND flash. Then these are the numbers that you could look at. Just keep these numbers in mind and then compare with the numbers that Kalyan may share tomorrow, on day after tomorrow. Okay. And you can actually find out read speeds, the same kind of formula that we used when we were working on DRAM, when finding the peak bandwidth over there. Exactly the same way, you just need to understand how the page is organized, what kind of time it takes for data transfer, what kind of time it takes for command transfer, number of cycles for command transfer, and so on. And you can arrive at read speed, write speed, and erase speed. And you see erase speed is much, much faster. Why?
Complete block is erased.
The complete block gets erased in one go. So the total amount of time you need is lesser. However, realize that you need 2 milliseconds to erase. You need 2 milliseconds to erase. But because now the number of times this erase has to happen is lesser, overall erase speed is much higher. Okay. Now a quick comparison between NAND and NOR. NOR is very high speed random access and byte programming. Over here, high speed programming, high speed erasing, small block size, but it has very slow random access. Additionally, byte programming cannot be done. For the NOR, the programming and arrays are also slow. And NOR Flash could be suitable for replacement of EPROMs, and because these are usually smaller in size, whereas NAND Flash can actually be used as a data memory. All the SD cards that we use, they're all NAND Flash because it's dense, therefore cheaper. Okay, any questions?
Sir, in page register, what will be the mechanism of burst access there? In DRAM, we saw that first we give the row, we do row decoding, and then we give columns address, and we taking the burst. But here, what we will do? How we will do?
So all those schemes that we looked at in DRAM can also be explored to be used here, because they are not linked to data to the DRAM per se, are they? No, they are all about inter-chip data transfer. So all those schemes you can put over here also in control by controlling it.
Okay, sir. One more confusion then, sir. We initially saw when we see the timing diagram, we were initially sending the column address, and then we are sending the row address. So would it create any rates condition during the burst mode access?
So again, you would want to do it according to what is the requirement there. Okay. So यहाँ पे when you select one particular row, you are actually selecting the entire page, reading the entire page anyways. So you may not need any further thing for burst mode access, something like inside the memory. आप उसको जब अपने नीचे के SRAM के plane पे ले आए, when you brought it to the plane of your SRAM, then you can decide whether to how fast or how slow to read there.
ओके ओके, मतलब पहले SRAM के प्लेन पे ला देंगे, फिर उसके बाद बर्स्ट मोड ऑफ कर दिया.
Okay,
got it.
So guys, all the best. I would say be prepared for the session on day after tomorrow. I want you to be very interactive, ask questions, and we'll be meeting physically. Just reminding you, we'll be meeting physically on 7th at 11:30 p.m. in A007 in the R&D block. Okay. All the best.
Okay, sir. Thank you, sir.
Yeah. Bye.
Thank you, sir.